So today we're going to kind of branch out with what we started doing yesterday into finding exponents where there are common bases. Now yesterday we were doing uncommon bases, so I'm actually going to start there. So I'm actually going to start on problem 11. So in this case, this should look similar to the problems we were doing yesterday. So we saw a few ways to solve for a missing logarithm. For a missing exponent, and one is using a logarithm. So I can write a log on both sides of this example. So I'm just writing log. It's log base 10 by default, which is fine. Next, I'm going to use the logarithm law that says I can bring the exponent out as a coefficient. So this will become x log of 3 equals log of 81. And to get x by itself, I'm just going to divide the log 3 to the other side. So I'm going to get x equals log of 81 over log 3. Now there is another way to do this. Oh, I actually have to, I'll show you what the answer is. The answer is 4, but we'll do that with a calculator real quickly. So if I do log of 81 and divide that by log of 3, I should get 4. Now, in the classroom, you'll remember that I did something called log base. So to do log base, there's a general format you want to follow. That is, if you're given any base with an exponent, there can't be anything else here, so it has to just be a number to a power, equals a particular value. And that can be rewritten as log with that base with that particular value equals the exponent. So in this case, I could just rewrite the equation we have here as log base 3. So this is an alternative method for solving this problem. And it gives us 81 to find this exponent. So if I just use a calculator, I'll get x equals 4. Now this is more useful when you have a value where you can't make a common base. This particular problem, you can make a common base. And I'll show you the common base now. So to make 81 into a common base, I'm just going to break 81 down into 3 times 27. 3 is a prime number. 27 is going to be 3 times 9. And 3 is a prime number. And 9 is going to become 3 times 3, which are both prime numbers. So that means I can rewrite this as 3 to the x equals 3 to the 4th, which means in order for us to get the same value on both sides, this exponent has to equal this exponent. Therefore, x equals 4. So we just did this problem in 3 different ways. So one way is common base. One way is log on both sides. And one way is logarithmic form. So either one of these, any of these would work. Let's take a look at problem 14. Problem 14, there is no common base because 51 can only be written as 3 times 17. So we can't make that into a 6. So we can't use common base form. Now, for this one, we're just going to have to use log form. So we would just convert b to the x into equals y into log base b equals x. So that would be log of 6 equals log base 6 of 51 equals x. And you can just do this with a calculator. Otherwise, you can do log on both sides. So log 6 to the x equals log 51. Yet x log 6 equals log 51, or which would then become x equals log 51 divided by log 6, which is going to be mathematically equivalent to this expression. So I'm going to use a calculator. We are going to get a decimal in this case because that's what happens when you don't have a common base. You usually get a decimal. So if I do log of 51 divided by log of 6, we get x is equal to approximately 2.19. So I'm just going to go 2 decimal places, and I'm going to recommend you do that as well for all these problems. If I were to do it with log base, I have to go to math. So if your calculator has log base, it's in the math section. I'm going to type in the base is 6, and I want to get 51, and that should give us the same value of 2.19. All right, now this also works if the problem looks a little bit weirder. So like in this problem, it's not quite in exponential form. If you look here, the 5 in the front here shouldn't be here. So if you just divide that from both sides, you'll get 5 to the x equals 14, and then it's just like the previous problem we just did, so you can solve that the rest of the way on your own. And problem 18 is also similar, but it's not much more different than the one we just had, so this one I'm going to do with you entirely. This can be rewritten in log form as log with a base of 5 of 1000 equals 3x. So all I need to do to get the x by itself here is divide both sides by 3. So I'm going to divide both sides by 3 and get that x is equal to log of log base 5 of 1000 divided by 3. And I can use a calculator to get this. Or I can do log on both sides. So log of 5 to the 3x equals 1000, log 1000. I'm going to apply the exponent rule or the power rule of logs to bring the 3x out front. Again, this is just an alternative method of doing this problem. So now I'm going to divide the log 5 to the other side and get 3x equals log 1000 divided by log of 5. And then to get x by itself, I'm going to divide that expression by 3. So this is mathematically equivalent to this answer. So if there's something extra after doing the calculation, you might have to divide or subtract or something afterwards. All right? Anyways, these are for the problems that don't have a common base. So let's take a look at the problems that do have a common base. So what I mean by a common base is that if you're given two numbers and they have the same prime factorization, or they're made up of the same values, we can write them in order to find their exponents. So here's what I mean. So 256 is equal to 2 times 128. 128 is equal to 64 times 2. Every time I get a prime number, I'm taking note of what it is. So I have two 2's so far. 64 is going to be equal to 2 times 32. 32 is going to be equal to 2 times 16. And 16 is going to be equal to 8 times 2. 8 is going to be equal to 4 times 2. And 4 is going to be equal to 2 times 2. And both of these are prime numbers. All the numbers here are now prime numbers. And if I were to count them, let me just remove this from the screen. We don't need it right now. If I were to count these, I have 1, 2, 3, 4, 5, 6, 7, 8 2's. So I can rewrite 256 as 2 to the 8th power, and I'm going to bring the x plus 4 inside of a parenthesis. I'm going to do the same thing for 64. Now, 64 is 2 to the 6th power. You can just break it down. We've actually kind of done it already. So 64 starts here. So if I were to look at this branch here, I can count 3 to 8 is 6 of them. So I'm going to put the 2x minus 2 inside of a parenthesis. So that means that these two numbers could have been represented this way as well. So that means 2 to the 8x plus 32 is equal to 2 to the 12x minus 12. So that's just distributing the exponents. So now to get the same value on both sides, this exponent has to equal this exponent. So I could just solve that equation. So 8x plus 32 equals 12x minus 12. So I'm going to subtract the 8x to the right side, and that'll give me 4x. Then I'm going to add the 12 to the other side. and that's going to give me 44. And then if I just solve this, I'll get x equals 11. Now, that means if I plug 11 into both the x on the left side and the x on the right side, I should get both sides to equal the same value. Now, they are going to be really big numbers, because 256 to the 15th power is going to be massive, so we won't actually be able to use a calculator to really see what that number is, but that would be how it would work. Next problem I wanted to look at is problem 6. And the reason I wanted to look at this one is because the number that we were going to divide by here is a little bit weird. So I'm going to do for the smaller number, just for explanation, I'm going to divide this by 2. So I'm using a calculator on the side here. So 1296 divided by 2 is 648. That divided by 2 is going to be 324. So I have two 2's already. If I do it again, I'm going to get 2 to the divided by 2, 162, which will then break down into 2 times 81. And 81 is not divisible by 2. And that doesn't mean we did this wrong. It just means that we have to break down 81 now. So I'm going to break 81 down. So I'm going to go this way. I'm going to keep going this way. So that's 3 times 27. 27 is 3 times 9. And 9 is 3 times 3. So what happened here is I have 4 3's. And I also have 4 2's. So what that means is I can rewrite 1296 as 2 to the 4th times 3 to the 4th, which is the same thing as saying 6 to the 4th. So that really meant is that this problem, the common base is probably 6. So if we take this problem, it's going to be, I'm going to break down 776 by 6's. Maybe I'll get there much faster this time, because I won't have to do this twice. So I'm just going to divide by 6. So 7776 divided by is going to equal 6 times 1296, which is a good sign, because that means this is really 6 to the 4th times 6 to the 5th. I'm sorry, 6 to the 4th times 6 to the 1. So that means the left side is really 6 to the 5th power. I'm going to put inside a parenthesis 3x minus 10 from the exponent. This is going to equal 6 to the 4th power, and in a parenthesis I'm going to put x plus 4. So I'm just going to solve the equation. 15x minus 50 equals 4x plus 16. So I'm going to subtract the 4x to this side. I'm going to get 11x. I'm going to add the 50 to the other side. I'm going to get 66, and x equals 6. So sometimes the numbers aren't prime numbers, so you just have to figure out what the common base is. In this case, it was 6. All right. Just going to go over 2 more problems, and then the rest are going to be yours to try. Number 7 works exactly the same. It's just that this particular one, as you'll notice, it's 1 over 128. That just means that the exponent is negative. So this is actually, they're both powers of 2. So 128 is 2 to the, 128 is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, so that's going to be 2 to the 5th. Times 2 is going to be 64, times 2 is going to be 128, so that means 128 can be rewritten as 7 2's, so this is actually going to be 2 to the negative 7 power. Okay, I'm going to put in that negative 5x plus 8. This is going to be equal to 2 to the 5th and a negative x plus 3. We're just going to solve for the exponents again. So that's going to become 35x. That's just from the negative 7 times negative 5. Negative 7 times 8 is going to be negative 56 equals negative 5x plus 15. And if we solve this, we should get the correct exponent. I'll leave that for you to try. And number 8 is very similar. We're just going to change 25 here into 5 squared, and we're going to get, this is going to become a different exponent. Now, we don't need to change the one on the left because they both have a common base now of 5, so we're just going to solve the numerator. I'm sorry, the exponents. So negative 2x squared plus 10x equals 20x plus 12. Now this is a quadratic equation, so the reason these are here is to remind you of how to solve quadratics. So I'm just going to move everything to the left side. So the negative 2x squared is going to stay the same. I'm going to subtract 20x to the left side and get negative 10x, because 10x minus 20 is going to be negative 10. And then a move, so that's just this, minus 20x minus 20x. And that's going to give us the negative 10x. I'm also going to subtract the 12 over to the other side as well. So it's going to become negative 12 equals 0. And now it's a matter of factoring. So firstly, there is a GCF here of negative 2. So I'm going to divide everything here by negative 2 and get x squared plus 5x plus 6 equals 0. This can be factored very easily. So this is going to be x plus 2 and x plus 3, because 2 times 3 is 6, and 2 plus 3 is 5. And that means the solutions to this problem are x equals negative 2 and x equals negative 3. So these are the x values that solve this equation. All right, the problems all mostly came from Delta Math, so I would recommend that you do the Delta Math assignment first for practice, and then ask me additional questions if you need help